So now we're going to launch a projectile at an angle, and everything's going to be the same. We're just adding an additional step. When it's launched at an angle, we're going to see that we have to figure out what the y component of initial velocity is and what the x component of velocity is. And then we just go through it like we've been solving all our other problems. And so we'll see that. We'll do a couple of examples here. So this one I'll go through pretty slowly and show you all the steps, and then I'll give you a couple of examples where we go a little faster. So this problem says a projectile is launched upward with an initial velocity of 350 meters per second at an angle of 65 degrees with the horizontal. How high will it go and how far will it travel horizontally? So here's the situation here, and on a tester quiz from me, you would get a diagram with this that looks a little bit like this. So you have it launched upward at this angle of 65, that should say degrees, 65 degrees, and at the speed of 350 meters per second. And you're asked two things. You're asked how high will it go. So what do I know about this thing? I know it's going to go up and it's going to come down, and it's going to follow that nice parabolic path. And you're asked, well, what is this distance going to be? We'll call it delta y because it's a vertical displacement. It's the maximum vertical displacement. And you're also asked, hey, from where it's launched, how far will it travel horizontally until it ends? So you're asked to find delta x and delta y here in this problem. So again, our first step, I cannot say the initial velocity in the y direction, as I have been doing, is 0 because some of this velocity is upward. Some of it's sideways and some of it's upward. So my first step is going to be, in a problem like this, is to find the horizontal and vertical components of velocity. So find the x and y components of the launch velocity. And you have done this, not this particular problem, but you have, this is just a right triangle problem. This is just a trigonometry problem, and you have done this many, many times. So here we have a right triangle with a hypotenuse of 350, where theta is 65. Here's my triangle. I'm not going to put units in here. I'm just rewriting this. So we want to know, well, how fast is it going in the x direction? What component of this 350 is in the x direction, and what component is in the y direction? And just a little note, point a little something out, that this, I'm just putting velocity in the x direction because it's a constant. I don't have to put initial velocity, final velocity. It is a constant. Along the x-axis, along the horizontal, even though this is launched at an angle, along the horizontal, the velocity is constant. There is no force. This is a free fall problem. The only force acting on this object is its weight, the force that the Earth exists on it, and so the only acceleration is downward. Here I'm saying initial velocity in the y direction because the y velocity is going to change. As this thing goes up, the y velocity is going to change. So let me find this. And again, here I'm going to write out all the steps to solve this, and you might want to skip ahead if you already know how to do this. If you don't know how to do this, if when I go through this you're thinking, what is this? Go back to those reviews and look at the trigonometry review and make sure that you remember your trig. Here I have theta is 65. I know that 350 is my hypotenuse relative to theta. If I go across from theta, I end up with initial velocity in the y direction. That's opposite. And here, this is adjacent. So in order to find, let's first find the velocity in the x direction. Doesn't matter what we find first, but we'll find this first. What trig function am I going to use? Well, hypotenuse is known, theta is known, and I want to know adjacent. So what function has adjacent and hypotenuse? And that's cosine. So I know the cosine of theta is adjacent over hypotenuse. I know that the adjacent side is the velocity in the x direction, and I know that the hypotenuse is just the launch velocity. It's not the y velocity, it's the launch velocity. So if I want to know what the velocity in the x direction is, I'm going to multiply both sides by the initial velocity, or by the hypotenuse here. And I end up with velocity in the x direction is the launch velocity, which is the hypotenuse times the cosine of the launch angle. Velocity in the x direction is going to be that initial velocity is 350 times the cosine theta here is 65. And I am going to get, when I solve this, 148 meters per second. What does that mean? It means that this thing is traveling 148 meters per second horizontally for this whole event. So what's going to decide how far it goes horizontally is just how long it travels at that speed, just how long it's going. And the event starts when it's launched, and the event stops when it's when it lands, rather. And for this whole time, it is going to be going 148 meters per second. So if it travels for 1 second, it's going to travel 148 meters. If it travels for 10 seconds, it's going to go 1,480 meters. So time is the only factor. This is a constant velocity still in the y direction. Now I'm going to find the initial velocity in the y direction using trig also. That's this. This would be the opposite side. So here's theta. I want to know opposite given hypotenuse. What function has opposite and hypotenuse? And that would be the sine function. The opposite side, opposite theta here, is the initial velocity in the y direction. And the hypotenuse is the launch velocity. I'll put a little L there so you know it's the launch velocity. So initial velocity in the y direction is the launch velocity times the sine of the launch angle. I can substitute launch velocity 350, launch angle 65. And again, if you're looking at this and feeling anxiety and you don't know what I'm doing, go back and watch those videos where I show you how to do this. This is 317 meters per second. So my first step is to find these two values. On your homework on a test or quiz, show me enough work where I know you didn't just copy this off the kid next to you. So show me something. Show me what numbers you used. If you show me this calculation, that would be fine. Just show me something. I think we're at a point where we've done this enough where I'm pretty confident you know how to do this. You know how to use these trig functions, but you still need to show me something. So I should know that you're using cosine. I should know what calculation you did, and then you can just give me the answer. I'm not going to be a real stickler about showing every single step on this one. All right, so how high will it go? Let's answer that question if we can. How high? How high is asking what is the maximum vertical displacement? We can call that y max. The maximum y position, the maximum vertical position, if we assume it started at 0. How high does it go? So what do I know about an object when it gets to its maximum altitude? I know that for that instant, its velocity in the y direction is 0. It stops. If I throw a tennis ball up in the air, it slows down as it rises. It goes slower, slower, slower. It stops when it gets to its maximum height for an instant, and then it reverses direction and falls back down, and it gains speed. So I know, I'm going to list my variables here that I know. I know that at its maximum altitude, at y max, the velocity in the y direction is going to be 0. I know that the initial y velocity, this thing here I calculated, and I know that that's 317 meters per second. In what direction was it launched? It was launched upward. So I'm going to put that arrow there to remind myself that velocity is a vector, and I have to denote the direction of a vector by giving it a positive or a negative sign when I do my math. So the initial velocity is upward. It's 317. What do I always know in a free fall problem? I always know acceleration is acceleration due to gravity, and it is 9.8 meters per second every second downward. So here I have one vector pointing up, and I have one vector pointing down. And I'm going to indicate mathematically that these are in opposite directions by giving them opposite signs. I can make every vector pointing up negative and every vector pointing down positive, or the other way around, it doesn't matter. I am going to make downward negative because I think of downward as negative. So if I had to choose, I would just make this negative. So in my problem, in my frame of reference that I'm setting up, anything pointing downward is negative, or traveling downward is negative, and upward is positive. So I take care of that sign there. And I want to know delta y, and I have enough information to solve for it. I know final velocity, I know initial velocity, I know acceleration, and I want to know delta y. You have solved problems like this before in just regular kinematics when it was one-dimensional. So let's do that. What equation has final velocity, initial velocity, acceleration, and displacement? And it is this one. V squared equals V naught squared. I'll put my y's here. Plus 2a, I'm going to put 2g. Acceleration here is acceleration due to gravity. I'll just write g. Delta y. Delta y is displacement. Delta x is displacement. Delta y is displacement vertically. And so I want to distinguish this between this horizontal displacement. That's all. I want to isolate delta y. The first thing I'm going to do is subtract v naught y from both sides. So I get vy squared minus v naught y squared. And a lot of you just stop squaring things. You just let that square drop off as you go through the problem. Be careful not to do that. Is 2g delta y. I want to isolate delta y. I'm going to divide both sides by 2g. 2g over 2g is 1. And so I'm going to move my work over here. I end up with delta y equals final velocity in the y direction squared minus initial y velocity squared over 2g. Now I'm going to substitute my numbers into that. I'm kind of going right to left here. Sorry about that. Final velocity is 0 squared minus the initial velocity was 317 squared. Notice I put those squares on the outside of the parentheses because I need to square the units too to make them come out right. And I'm going to watch my sign on this. Now this is something where you guys might be able to get the right answer with the right sign without showing me that you put the numbers in correctly, and I still knock off points if you do that. So it's worth noting here that you're squaring this number positive 317. And then whatever you get when you square that is going to be negative. You're going to have a negative numerator, 0 minus the square, and you're going to have a negative denominator, which means you're going to have a positive displacement. So the displacement is going to be, when I do this math, 5,127 meters. That's quite a displacement, right? So it's going to go a little over 5 kilometers up in the air if you launch it at 350 meters per second. So I found this part. How high will it go? I solved that part. Now I want to know how far will it travel along the horizontal. So let me get rid of a lot of this work, and we'll go back and we'll solve that part of the problem. So I erased all that other stuff, and I put it, what I had calculated into this table here. Along the horizontal, it's traveling at a constant velocity of 148 meters per second. Along the vertical, its initial upward velocity, so the vertical component of this velocity, the launch velocity was 350 meters per second at an angle of 65 degrees upward, and the vertical component of that was 317. This is a free fall problem. We assume the only force acting on this is the force due to gravity, and therefore the acceleration would be downward. It is always downward in a free fall problem. G is always downward, and it is 9.8 meters per second every second. Since initial velocity is upward and acceleration is downward, I need to give them opposite signs. All vectors pointing down need to have the same sign. All vectors pointing up need to have the same sign. So I chose to make downward negative. Now, what else do I know? I want to know how far it'll travel. My unknown is delta x. And we know in this constant velocity problem that the equation that I'm going to use is the velocity in the x direction is displacement over time. If I want to know displacement, I need to know the velocity in the x direction, which I do know, but I also need to know time, and I don't know that. So I need to calculate time. So this is going to be just like what we did when we launched things horizontally, when we started working on these two-dimensional motion problems. I'm going to find time using my y information. But let's look at this. Let's think about this. What do I know in the y direction? We know initial velocity. I know acceleration. What else do I know? Well, I know that it started here. Let me get a new color. I know that it started at this position and it ended at this position. And in terms of how far it rose or fell horizontally, that distance is 0. The delta y here, I know, is 0 meters. It landed at the same height from which it was launched. This is the same situation as if you threw something up in the air let's say you throw a ball up in the air. Here's your hand. Here's a ball. And you throw it up in the air and it slows down and it stops and then it comes back down and it lands right back in your hand. Well, what's its vertical displacement? Well, this is the position where it was launched, position Y, and it landed. The event ended. It was back at position Y again. So its displacement 0. Same thing with this. Forget about the fact that it moved sideways. It moved up to this point and it moved right back down to its starting point along the vertical. So delta Y is 0. So using this information, can I find time? Sure. Can I find time? Remember, the time for this event is the same. The time it took to go up in the air and return to its launch height was the same as the time it took to move horizontally, however far it moved horizontally. So time is the variable these both have in common. Can I find time if I know V naught, initial velocity, acceleration, and displacement? And I can. And imagine that we're going to use this equation here. Delta Y is V naught T plus 1/2 GT squared. But wait a minute, you say. V naught is not 0. V naught is 317. And we've managed to solve these things without having to use the quadratic formula, which we really haven't gone over at all in class yet. But we've managed to solve these things by getting rid of this V naught T term. And we can't get rid of it now because we can only get rid of this if V naught is 0. V naught is not 0. Therefore, you have to keep this term, V naught T. So, oh my goodness, what do we do? Well, something else is 0, right? And that is this delta Y. Delta Y is 0. And so will that let me escape for another day from using the quadratic? It surely will. So delta Y is 0, its displacement 0. So I can write 0 equals V naught T plus 1/2 GT squared. I'm going to put V naught Y here. Now, algebraically, you can manipulate this however you want, but you can, I'm going to bring this V naught T term over. So V naught T plus 1/2 GT squared minus V naught T is just leaves me with this 1/2 GT squared. So I'm going to subtract this from both sides. 0 minus V naught T equals negative V naught T on this side. V naught T minus V naught T is 0. So I end up with 0 plus 1/2 GT squared. I don't have to write the 0. So I get this equals 1/2 GT squared. And now look what I can do. I can divide both sides by T. Negative V naught T over T. T over T is 1. So I end up with just negative V naught on that side. When I divide this by T, I end up with my T squared just becoming a T. So I end up with negative V naught equals 1/2 GT. I'm trying to find time. I need to find time, remember, in order to find my displacement. So that's what I'm still doing. I'm going to multiply both sides by 2. Then, oops, look at that. I tell you not to do that, and I just did it. I did that on purpose, so you'd feel better if you made a mistake like that. Get T by itself. I'm going to divide by G. T equals negative 2 V naught over G. Let me substitute. Negative 2 times V naught is upward. It's 317 meters per second. G is downward, so it's negative 9.8 meters per second every second. Again, the signs matter. So time ends up being positive, which it should. And when I solve for this, I get 65 seconds. This thing's going to be up in the air for a little more than a minute if I launch it. So in 65 seconds, if it goes along the horizontal 148 meters every second, in 65 seconds, it's going to go 65 times 148. I have that set up all over here. Delta X equals 148 meters per second times 65 seconds. And when I put that in my calculator, I get 9620 meters. So that is how far it will travel horizontally.